Okay, so how is everyone today? Good, I hope. It's rainy. Today's the 21st. And let's cover what, just recap what it was that we did last time. Last time we talked about two different ways to come up with the equation for a line. One of them was the point slope. It is so called point slope because that is the data that you have. So it says, supposing you have a point on the line x1, y1, and also a slope m, then the equation of this line is what? What's the equation of the line? That's the one that goes y minus y1 is equal to m multiplied by what? Very good. X minus x1. And then, visually, what that's saying is that, well, we've got the usual axes, x, the horizontal axis, y, the vertical axis. We've got some point, x1, y1, is known to be on a line, and this line is known to go through that point with slope m. Okay. The other main one that we had is called slope intercept. Well, in this case, what you have is that you have the slope. The slope is m. And what else do you have? A y-intercept. Yeah, I wish the name of this thing, instead of calling it slope intercept, I wish it were called slope y-intercept. To get rid of that ambiguity. So the slope m and y-intercept 0b, in such a case, what is the equation?
Y equals mx plus b.
Very good. Y is mx plus b. And then visually and conceptually, it's quite similar to the previous one. But what's the difference between these two cases? Because we still have a point and a slope. But what? Right. But in this case, it's not some point that's just anywhere. It's a point that we consider to be special because it happens to be on the y-axis. Okay. Any question about that? Yes?
Would you show another example of point slope?
We're gonna.
You would ask.
Yeah, we're gonna do one right now. Because we're starting section 2.2, or is it 3? I think it's 3 actually. 2.3. It's called something like linear models. Which is to say that we're going to do lines, just like we were in section 2.2, but now they're going to be couched in terms of word problems. right? Which makes it just that much more fun, right? The lines were fun, word problems are fun. You put them together, twice the fun. By the way, someone asked, that symbol, S with a circle through it, means section. It's pronounced out loud as section. Which to some of you is obvious, but I'll let you know that I actually didn't get that figured out until, like, I think after I had a PhD, right? I had no idea what that meant. Because where do you look it up? It's not in the dictionary. It's not in the S's. At least not in the dictionary I looked in. Okay. So let's have an example. Suppose the student population of UTD grows linearly. That's not true, but for this exercise, we're going to hold that to be true. Currently, in year 2018, the student population is 27,000. My understanding is that that's pretty close to accurate. Fine. Now, this next thing I'm going to say is just made up. Suppose that in year 2000, student population was 11,106. 11,106. So that's the setup. And here's the requests. So first request. Find a linear model for student population in variable p in terms of year t. I want you to, when you find that linear model, I want you to solve for p. The next request, after you've done that, will be to verify your linear model by plugging in known data. Three. Find the student population in year 2010. And for find the year when the student population is 40,000. Okay. So we haven't done any calculation yet, nothing like that. But for the time being, is there any question about the statement of the exercise? Yes?
Is a model the same thing as an equation?
Yeah. Okay. So now, before we go about answering these 4 requests, I want to make sure that everyone understands the idea. So in the first place, I want to point out that all the stuff that we've done with lines so far, at least finding equations for lines and things like that, what has been the names of the variables? X and Y. But that is not the case in this exercise. What is the name of the variables in this exercise? P and T. So you're going to have to, translate your knowledge with X, Y in terms of names X and Y into these names, right? Good. So that's one thing. And I also want to make sure that you understand the concept before we set out trying to calculate, because otherwise you can just get lost in the calculation and not really understand what's going on. So we have conceptually an axis. Is this an XY axis? No, right? I have no idea what X's and Y's are. In this exercise, we're talking about P's and T's. So, well, which one of them is the P axis? The vertical one. This one is P. Okay, so by process of elimination, T is the other one. The way you can tell that is by the statement of the exercise. It says, the statement of the exercise says, model that one in terms of that one. So the next language I'm going to say is not used in our book, I think, but it's somewhat common that many of you, if not all of you, have seen before. So there's this notion of an independent and a dependent variable. So which one is which? Time is independent. So this is the independent variable. And then this one is the dependent variable. Dependent. Okay. So conceptually speaking, here's the space. T is horizontal, P is vertical. We were given 2 points that are somewhere on this plane. What 2 points were we given? Okay. Okay, so here's some point. So you're saying that year 2018 and population 27,000 are a point. Which one do I write first? The year, right? The year goes first because, well, that's the first axis. Okay, so 2018. And then 27,000. What is another point that's known? Right, that one. In the year 2000, the student population was 11,106. So relative to this point, should it be left or right? To the left. How can you tell it should be to the left? It's a lesser year, right? And similarly, relative to this point, should it be down or up? Should be down because it's a lesser population. Okay. (2000) and population 11,106. And the statement of the exercise says that it is the case that population grows linearly with time. So the plot of population somehow looks like that, if I could draw a straight line. Any question about the idea? Okay. So, fine. Let's go about answering. So, for part 1, so it says find a linear model for student population P in terms of year T, solve for P. In the language of the previous section, what that's saying is find the equation of the line through these 2 points. Okay? So find the equation of the line through the 2 points. All right. Now we have 2 ways to find the equation of a line. One of them, we named them both out at the top of the previous page, right? One of them is called point slope, and the other is slope intercept. So my next question to y'all is that, well, should we use the point slope way, or should we do the slope intercept way? Point slope? Why point slope? Right. So in the end, you really can only use the slope intercept form if you have an intercept already. So we're going to use this one. Because neither point was an intercept. Specifically, was a y-intercept. Questions where one of the points is a y-intercept is sort of like an easy mode question, right? It makes your life a little easier. Fine. So now I'm a little bit concerned because, well, the point slope equation, in order to use it, you need a point and a slope. That's what you need. But it appears to me that what we were given was a point and a point. So I guess we're just out of luck. Ah, okay, we can calculate the slope first, right? Okay, fine. So we'll find the slope. And if you look through the previous exercises, lecture notes and things like that, the very next thing that I wrote on those exercises was I wrote delta x equal something or other, delta y equal something or other. Am I supposed to write delta x? No. Right. Delta x makes no sense. It makes no sense because, well, there's not an x in this exercise, and delta y doesn't make sense because there's not a y in this exercise. It would be the same kind of thing that, well, if you had a significant other, and your significant other was named, I don't know, Kelly. That's a name that could be anyone's name. Their name's Kelly, and then you refer to them as I don't know, Kevin. Does it make a difference? Yeah. Why are you calling me Kevin? Right? What are you doing? All right. So, delta t and delta p. Delta t, that'd be 2018 minus 2000, which is 18. And delta p would be what? Right, 27,000 minus 11,106. 27,000 minus 11,106 is 15894. So now, this exercise and talking about it and dealing with all of it, it's going to take most of the class. I recommend you get out your calculator and follow along. The reason is because you're going to have to do something just like this in a week's time. And it would be really sad if that were the first time you were trying to use your calculator for this purpose, and you couldn't answer the question because you weren't familiar with it. That'd be sad. Fine. So now, we can't use x's and y's because that's not part of the exercise, but still, the conceptual things of rise and run are still valid. Which one of these is which? Good. So t is the run. That's what's going horizontal. And delta p is the rise. All right. So then slope is the ratio of these things. So which one goes in the numerator? The rise. Right? So it should be delta p divided by delta t. Okay, so that means into the calculator we need to plug 15894 divide by 18. Okay, so what's that going to be? 883? So, in the class, I usually try and make silly numbers show up like 1314 because that's the course number. But what's 883? That's UTD's number, right? Have you noticed that all the phone numbers start with 883 and the bus route number is 883 and a lot of other things are 883? Why is that? Because if you look at a telephone and you look at on the keypad, number 2 says ABC, number 3 says DEF, blah blah blah. And if you type in UTD into the phone, what is it? 883. Funny. Hilarious. So in the exercise, what does 883 mean? How do you? I agree that it's the slope of the line, but that's a little bit abstract. What does it have to do with? Right. So this means that we, in a sense, the population increases by 883 students per year. All right. So we found the slope. Now we're trying to find the equation. So which point are we supposed to use? Either one, right? So it doesn't matter which one you use. So would someone please decide which one are we going to use? The 2018 one? Okay. 2018, 27,000. So we'll use that. Now, in abstract terms, when you're using x's and y's, that's the point-slope equation right there. But using what is the point-slope equation using p's and t's? Right. P minus P1 is m multiplied by t minus T1. So now it's just a matter of plugging in all the things. So P minus 27,000 is equal to 883 multiplied by T minus 2018. The instruction says solve for P. Okay, so let's make it look nice. So 883 times 2018 P minus 27,000 is 883 T, and then subtract. Okay, 1,781,894. Okay, then what do we need to do to solve for P? Add 27,000. Okay, so solving for P, 883 T, and then subtract 1,754,894. Wow. Unexpected, right? Or, you know, most of the time, at least when we're first dealing with a concept, like when we were first dealing with equations of lines, you know, you've got to have some numbers show up. Usually I arrange matters so that, you know, they're fractions, maybe with little, you know, like 2/3, you know, something like that. Or if the numbers are integers, then they're usually between -20 and +20 or something like that. But here's you know, not that case. So that's the answer to part 1, a linear model. What was part 2? Verify it, right? Which is to say, this linear model is on offer. You're saying that, well, this is a linear model for the data that you gave. The way that we verify that that's true is we plug in known values. Okay, so let's plug in the point 2,000, 11106. So if we plug in this point into the model, what do we expect? Should be true, right? Should be true. Fine. So 11106 equal 883 multiply 2,000 subtract 1,754,894. Okay. Success. 11106 equal 11106. All right. So does that mean that we for sure got it right? No, because something else could, something could be going wrong. So let's be clear about what could be going wrong. So the story gives us 2 points. Those 2 points. What did we just verify? We verified that we're going through that point. That's good. But what could be going wrong? Yeah, we might have the slope wrong or something, right? We could be going through that point, but maybe the line that we actually have is doing that, or that, or what have you. So when will we know that we have it right? When we verify the other point. Then we'll know that it's right. So at the point 2018, 27,000. Well, now the equation is 27,000 equal 883 multiply 2018 subtract 1,754,894. Yay. Got it. So if either one of those equations had been false, that would say, oh, I made an arithmetic error. Either up here when I was computing the model, or right here when I was verifying it. There is, if either one of these is false, then it is necessarily true that you've made an arithmetic error somewhere. Good. Any question about this? So now, I want to try and keep you from falling into an error, and that is that on questions like this, students, about a third, maybe a fourth of students really chafe at the instruction to verify that your model is correct. Like, no, I'm not going to do that. Okay, well, okay, that's, you know, you put yourself at the mercy of the grader if you take that stance. But at the other, on the other hand, what I want you to think of is like, well, what if you're working for a business, and the business is saying, you know, oh, I heard you took college algebra at UTD. I'd like for you to compute a linear model for our profits or whatever, and they're in terms of millions of dollars, and then you make a little calculation and you turn it into your boss. And the boss says, okay, great, now can you show me where you verified your work? And you say, I don't verify my work. I mean, does that sound like excellent? No, it sounds terrible, right? You're fired, get out of here. Same thing here. Good. For number 3, what was the request was, find the student population in year 2010. Okay, so that's the statement in English, but could someone translate that into a more mathy request? Okay, plug in t equals 2010 and do what? And solve for p. Okay. Plug in t equal 2010 and solve for p. Now, we're going to go on and do a calculation. Okay, and the calculation is pretty straightforward. But before we do that, I want to make sure that that the concept is clear. The request was find the student population. What's the name of that variable? P, right? In the year 2010. And so what variable does 2010 correspond to? T. So it's saying plug in t equal this value and find the other variable. Okay, good. Fine. So P is equal to 883 multiply 2010 subtract 1,754,894 and put that in the calculator. the answer is 19,936. Okay. Any question about arriving at that number?
I'm kind of lost right now.
Okay. So we have this linear model. P is 883T. Subtract 1 million, blah, 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 big number. It agrees with the statement of the exercise. In the year 2018, the population is 27,000. That's what this second line is saying. And in the year 2000, the student population is 11,106. That's what the first line is saying. So we've got a model. We plug in, so those are the populations at specific points. Now I'm asking about the population at a different point. So we were given the population at 2000, year 2000. And we were given the population at year 2018. Now the request is, well, what about the population at this other year, 2010? Well, use your model and plug in 2010. And that's the answer. So now I want to make an aside. The aside is that what if student makes a math error, say an arithmetic error or a calculator error. And gets the following. Gets P equal 31,253. Well, in the first place, that it's not right, right? So you're probably not going to get full credit for that answer. It's not right by virtue of it not being 19,936. But I claim that, well, it's not right, but it's not right in such a way that much of the credit for this exercise needs to be taken away. So it's wrong, but in a big way. So let me be clear about what I mean. Suppose if I requested you to go to the grocery store and get a red apple. Well, if you went to the grocery store and came back with a green apple, then, okay, yeah, well, plenty of partial credit for that. At least it was an apple. It wasn't red. I asked for a red one, but okay, at least it was an apple. Or, if the instructions were, please go to the grocery store and get for us a red apple so that we can eat it, we can share it. You go to the grocery store and you get a red apple, but it's plastic. Okay, well, at least it was a red apple. Okay, partial credit, good. But if you go to the store and the request is, please go get us a red apple that we can share to eat, and then you come back with like a giraffe or something. What even happened? That doesn't even make sense. How did that occur? Okay, what I'm saying is that this number, 31,000, is like a giraffe. It doesn't even make sense, this number. So let's see why. The number, or the answer, P equal 31,253, is nonsense. Because, well, let's consider what this exercise is about. We're making a linear model. The first axis is time. The second axis is population. And we've been given 2 points. The 2 points that we were given were 2018. Sorry, the leftmost one was 2000, and then population 11,106. and the upper right point was 2018 with population 27,000. Those are the 2 points that we were given. And that corresponds to 2 points on the time axis. There's a point at year 2000 and another point at year 2018. Okay. The exercise states that this is a linear model, which means that there's a line going through these 2 points. There's a line going through those 2 points. And currently, on part 3, what time are we talking about? 2010. And can you see that that is in between the 2 times that we know? It's in between them. So 2010 is not exactly halfway. It's a little bit further than halfway. So we're asking about the time t equal 2010. So now, at time 2000, what was the population? 11,106. And at time 2018, what was the population? 27,000. So, if I ask you about the time 2010, and that's in between the 2 points that you were given in the exercise, then what needs to be true about the population? Right. It's got to be between these 2. If it's not between these 2, that indicates unambiguously that you don't really understand what you're doing. Okay, it means that you're just sort of calculating, but you're not really sure what it means. So this point is the point we're looking for. Right there. So that one is the correct answer. So what I'm telling you is that, if I send you to the store for a red apple and you come back with a green apple, well, that's kind of like if you made the wrong answer, but at least it was between 11,000 and 27,000. Okay, it makes sense, at least in that way. Responding with 31,000, which is way up here, 31,253. I mean, it's not right, but it's not right in such a way that it's not even in here. So your answer must be in this interval to even begin to make sense. So to say it another way, and yet another way, suppose that you made a calculator error. The correct answer is 19,936. Suppose that you said it was 20,936. Well, it's not right because you made a calculator error. But at least it's between 11,000 and 27,000, right? Similarly, if I were to ask you about, what's the population, when would the population be 40,000? That was the next question. We don't have time to answer it because we're going to have a quiz in a second. But when you should be able to tell me where, generally, in time that should occur. Where, when, at what time is the population going to be 40,000? Sometime after 2018, right? If you respond to me and say like 50, that's not even close. It's not even reasonable, right? 50 is way over there. Okay, good. So now let's have a quiz.